Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The middle of the 19th century found the science of chemistry in a state of profound paradox. Its practitioners commanded an impressive and growing power to transform matter, yet they laboured under a fundamental limitation. The established methods of analytical chemistry, relying on precipitations, titrations, and weighings, were formidable tools for bulk substances. They became cumbersome, destructive, and often profoundly ambiguous when confronted with the great challenge of the trace element, identifying a minuscule quantity of a substance within a complex mineral matrix, or distinguishing between chemically similar elements like the alkali metals, remained an intractable problem. Parallel to this terrestrial challenge was a celestial enigma. 2 generations earlier, the meticulous optical craftsman Joseph von Fraunhofer had passed sunlight through a prism and observed something astonishing. The beautiful rainbow of the solar spectrum was interrupted by a cryptic pattern of hundreds, then thousands, of fine dark lines. He catalogued their positions with extraordinary precision, treating them as fixed cosmic markers, yet their origin remained a complete mystery. These 2 disparate problems, one in the crucible of the chemist's laboratory, and the other in the silent light from the sun, waited a single, unifying solution, a solution that when delivered from Heidelberg was by 1050, the work of Gustav Robert Kirchhoff, a theoretical physicist of penetrating insight, and Robert Wilhelm Bunsen, a peerless experimental chemist, emerged from a fertile intellectual landscape. The idea of using light as an analytical tool was extant. Flame tests were a common, if crude, qualitative guide. Chemists knew the lithium salts lend a flame a carmine hue, strontium a brilliant crimson, and sodium an overwhelmingly intense yellow. These observations were suggestive, though they offered poor certainty. Mixtures produced a confusing cacophony of colours, and the subtle differences between elements were easily lost to the observer's eye. Others, like William Henry Fox Talbot, had gone a step further, viewing these coloured flames through a prism and noting the appearance of distinct bright lines. He even proposed a future for what he termed optical analysis. The efforts of these precursors, however, were unsystematic. They lacked a robust methodology and a reliable instrument capable of producing stable, reproducible, and precisely measurable results. They saw the promise, but were unable to construct the necessary bridge from qualitative observation to quantitative science. It was Fraunhofer's own legacy of precision, his demonstration that a spectrum's features could be measured with mathematical rigour, that set the high standard any new method would need to meet. His silent, dark lines beckoned for an explanation, while the chemist's glowing flames called for systematization. The first pillar of the Bunsen-Kirchhoff revolution was physical, a masterpiece of purpose-built instrumentation. The spectroscope was an elegant synthesis of components, each designed to overcome a specific obstacle that had plagued earlier attempts. The foundation was Bunsen's own recent invention, the gas burner. This device produced a flame of very high temperature, with exceptionally low luminosity, unlike the flickering, sooty flames of alcohol or oil lamps which created their own complex spectra. The Bunsen burner provided a near-invisible, colourless thermal sage. Upon this clean background, the characteristic light emitted by an incandescent element could shine with unparalleled clarity. Light from the sample vaporized in this flame was then directed through a narrow vertical slit. This thin ribbon of light entered a collimator, tube with a lens that rendered the light rays parallel. This step was crucial for sharpness. By ensuring all light struck the dispersing element at the same angle, it prevented the smearing of colours and transformed what would be a blur into a set of crisp, discrete lines. This parallel beam then passed through a high-quality prism, which performed the critical act of dispersion, fanning the light out into its constituent frequencies. The resulting spectrum was viewed through a small telescope, which magnified the image and was frequently mounted alongside a second telescope containing an illuminated, calibrated scale. The entire apparatus transformed a fleeting visual effect into a stable, measurable physical phenomenon. With this instrument in hand, Kirchhoff and Bunsen advanced the conceptual breakthrough that formed the core of their 1859 paper, Chemical Analysis by Observation of Spectra. Their central assertion was as simple as it was profound. Every chemical element, when heated to a gaseous, incandescent state, emits light at a set of unique, characteristic, and unalterable frequencies. This bright line emission spectrum constituted an immutable optical signature, an elemental fingerprint. The spectrum, they argued, was an intrinsic property of the atoms of the element itself, a fundamental constant of nature laid bare by heat and light. Their paper provided immediate and incontrovertible proof. They turned their new device upon the vexing problem of the alkali metals. Where wet chemistry struggled, the spectroscope delivered unambiguous verdicts. Sodium, whether as a chloride, an iodide, or a sulfate, invariably produced its iconic, tightly spaced pair of yellow lines. Potassium, in any of its compounds, revealed a distinct line in the deep red and another in the far violet. Lithium displayed a brilliant, singular red line, entirely distinct from the crimson of strontium with which it was often confused. The ability to differentiate these elements with absolute certainty, even when present in microscopic quantities, within a complex mixture, represented a leap in analytical power orders of magnitude beyond the prior state of the art. The age of spectral analysis had begun, providing humanity with a tool of exquisite sensitivity to probe the elemental composition of matter. The immediate vindication of their technique arrived with breathtaking speed in 1860, while analysing mineral water from Durkheim. Kirchhoff and Bunsen observed two brilliant blue lines belonging to no known substance. This spectral signature heralded the discovery of a new alkali metal, which they named cesium, derived from the Latin cesius for sky blue. Scarcely a year later, a similar investigation of the mineral lepidolite revealed a pair of deep red lines, equally alien to the known catalogue of elements. This was rubidium, named for its characteristic ruby red emission. Through their method, they located new fundamental components of nature, demonstrating an analytical power that could pluck undiscovered elements from complex solutions based solely on the unique colour of their incandescent vapour. Terrestrial chemistry had a new, unerring guide, yet the instrument's terrestrial triumphs, while profound, were soon eclipsed by a far greater revelation. The conceptual heart of the 1859 paper lay in Kirchhoff's masterful generalization, a principle that became known as his law of thermal radiation. He deduced that for any material body, in thermodynamic equilibrium, the ratio of its emissive power to its absorptive power is the same for all bodies at a given temperature and frequency. A direct and powerful consequence of this is that an object will absorb light at the very same frequencies it emits when heated. The bright lines of an emission spectrum and the dark lines of an absorption spectrum were two faces of the same physical reality, one showing the light a substance creates, the other showing the light it subtracts. This elegant unifying principle provided the definitive key to one of astronomy's most persistent enigmas, the dark Fraunhofer lines crisscrossing the solar spectrum. Kirchhoff reasoned that the sun's intensely hot, dense core, the photosphere, radiates a continuous spectrum like any incandescent solid or liquid. As this light travels outward, it passes through the sun's cooler, more tenuous outer atmosphere, the chromosphere. The elements within this cooler gaseous layer absorb their characteristic frequencies from the continuous spectrum passing through, leaving behind a pattern of dark absorption lines. The celestial mystery resolved into a problem of terrestrial chemistry. Kirchhoff performed a decisive experiment of sublime simplicity. He passed bright sunlight through the flame of a Bunsen burner containing common salt, instead of the salt's bright yellow sodium lines filling in the corresponding dark Fraunhofer lines in the solar spectrum. Those dark lines grew even starker, more pronounced. The cooler sodium vapour in the flame was absorbing the same solar frequency that it would otherwise emit. The conclusion was inescapable and universe-altering. The sun contained sodium. He swiftly went on to identify the spectral fingerprints of iron, calcium, magnesium, and nickel in the solar atmosphere, proving that the stars were composed of the same fundamental matter as the Earth. With this discovery, the science of astrophysics was born, and the cosmos became an extension of the laboratory. The implications rippled through the scientific community, empowering a new generation of cosmic explorers. In Italy, the Jesuit astronomer Angelo Secchi, armed with a spectroscope attached to his telescope at the Roman College, began a systematic survey of the heavens. He classified over 4,000 stars into distinct spectral types based on the patterns of their Fraunhofer lines, creating the first stellar taxonomy grounded in physical composition. This work transformed astronomy from a discipline concerned primarily with celestial mechanics into one that could investigate the physical nature and evolution of the stars themselves. Meanwhile, in England, Norman Lockyer turned his spectroscope toward the sun during the total solar eclipse of 1868. He observed a brilliant yellow emission line in the solar chromosphere that corresponded to no element ever seen in a laboratory. With extraordinary confidence in the new method, Lockyer proposed the existence of a new solar element, naming it helium, from the Greek helios for the sun. For over 2 decades, helium was a celestial curiosity, an element known to exist 93 million miles away but absent on Earth. Its eventual discovery in 1895 within the uranium-bearing mineral clevate served as the ultimate confirmation of spectroscopic analysis. The spectroscope had unveiled what the universe was made of, but in doing so, it posed a deeper question: why? The spectral lines of elements were discrete, sharp, and followed puzzlingly regular mathematical patterns. 1885. A Swiss schoolteacher named Johann Balmer found a simple empirical formula that precisely predicted the frequencies of the 4 visible lines of the hydrogen spectrum. This mathematical regularity later extended into the ultraviolet by Lyman and the infrared by Paschen, was a profound clue. The structure of the atom itself seemed to be written in the language of light. This precise, empirical data from spectroscopy became the bedrock upon which modern physics was constructed. The challenge shifted from identifying elements to explaining the origin of their unique spectral fingerprints. The answer would require a complete overthrow of classical physics. It was Niels Bohr, in his 1913 atomic model, who provided the first successful theoretical explanation. He proposed that electrons could only occupy specific, quantized energy orbits around the nucleus. A spectral line was the light emitted or absorbed when an electron made a quantum leap from one allowed orbit to another. The frequency of that light corresponded exactly to the energy difference between the two states. The Balmer series was nothing less than the visible evidence of quantum reality. Thus, the journey that began in a Heidelberg laboratory with a modified lamp and a prism led directly to the core of 20th century science. Kirchhoff and Bunsen's work dissolved the ancient barrier between the terrestrial and the celestial, revealing a universe unified by common chemistry. It gave humanity a tool to read the elemental script of the cosmos and, in the patterns of that script, provided the essential empirical evidence that would force a revolution in our understanding of matter and energy. The 1859 paper represents a rare moment in history when a single new technique simultaneously unlocks the secrets of the atom and the stars, forever reshaping our perception of the universe and our place within its grand, luminous design.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.